The stick shaker screams, the nose pitches down, and a crew fights a ghost they can't see. Then silence over the Java Sea. 5 months later, above the Ethiopian plateau, the same alarms erupt, the same desperate trim wheel spins, and another jet slams into Earth. How did two brand new airliners, minutes after takeoff, lose to a force hidden inside their own flight controls? The answer wasn't a storm, a bomb, or a bird strike, but a line of code armed with a single, unreliable glance at the world. Buried from pilots, blessed by regulators, it could quietly seize the controls in the name of safety. The secret was not just what failed, but how a system designed to save an airplane was allowed to fly blind. In commercial aviation, disasters are supposed to rhyme, not repeat. Yet between October 2018 and March 2019, two brand new Boeing 737 MAX 8s fell from the sky minutes after takeoff in different countries, flown by different airlines, under different crews, leaving 346 people dead and a profession staring at a pattern it could not ignore. The near symmetry of Lion Air Flight 610 off Jakarta and Ethiopian Airlines. Flight 302 near Addis Ababa punctured a bedrock belief of modern safety, that layers of training, redundancy, and certification had made catastrophic design-driven accidents vanishingly rare. The question was no longer whether a single, unlucky chain of events could defeat a crew. It was why two did so in nearly the same way. Before dawn on October 29, 2018, Lion Air 610 lifted from Jakarta's runway and soon began to wander in altitude, a sawtooth trace on tracking screens watched by analysts and armchair observers alike. 13 minutes later, it hit the Java Sea, scattering wreckage across choppy water as fishermen and divers converged on bobbing life vests and twisted aluminum. Indonesia's National Transportation Safety Committee, KNKT, led the investigation. The flight data recorder was recovered within days, the cockpit voice recorder months later. Even in the early data, one theme stood out: repeated nose-down trim commands that the crew countered again and again. Within a week, the U.S. Federal Aviation Administration issued an emergency airworthiness directive, reminding pilots worldwide about the runaway stabilizer checklist, and Boeing circulated a bulletin pointing crews back to a memory procedure older than many of the airplanes themselves. For a time, the industry leaned on familiar explanations: maintenance lapses, training gaps, a low-cost carrier's culture. That fragile comfort lasted 132 days. On March 10, 2019, Ethiopian 302 thundered off Addis Ababa's high-altitude runway and, within 6 minutes, struck a field, carving a blackened scar into the plateau. The jet's black boxes were quickly flown to France's BEA for decoding. Early findings echoed Jakarta: a stick shaker at liftoff, aggressive nose-down trim movements, pilots struggling to level the airplane. Regulators reacted in waves. China grounded the MAX first on March 11th. Europe, Canada, and others followed. The FAA, increasingly isolated, grounded the fleet on March 13th after new satellite tracking evidence suggested uncanny parallels between the two flights. The repetition transformed what would have been a single tragedy into a systemic crisis. The idea that a software-driven behavior might be seizing control was no longer a whisper among engineers, but a public suspicion. Investigations widened beyond cockpit actions to the airplane's architecture and the assumptions embedded in its certification. The KNKT and Ethiopia's Accident Investigation Bureau probed design logic and maintenance history. The U.S. National Transportation Safety Board examined human factors pitfalls. A joint authorities technical review, led by former NTSB Chair Christopher Hart, audited the FAA's approval process. Congressional hearings extracted internal emails and timelines. Around the world, the invisible contract that passengers have with manufacturers and regulators, that complexity is tamed before a product enters service, had been breached, and the only path back ran through uncomfortable transparency. What went wrong, investigators would conclude, was not a single bad part or a rogue crew, but a convergence of misleading sensor data, opaque automation, and oversight decisions that underestimated hazards. To understand how those strands braided into catastrophe, we have to step back to the commercial chess match that set the program in motion. Boeing's rush to counter Airbus's fuel-sipping A320neo without starting from a clean sheet. When Airbus unveiled the A320neo in 2010, a re-engined fuel-sipping update to its workhorse narrow body, airline spreadsheets lit up. The promise was simple and brutal: double-digit percentage savings on fuel without retraining pilots or retooling fleets. By mid-2011, the orders were mounting, and in July, American Airlines announced a blockbuster deal that would lean heavily toward Airbus unless Boeing could match the numbers fast. Inside Boeing's Chicago headquarters and at the Commercial Airplanes Division in Seattle, the choice hardened into a deadline. A clean-sheet successor to the 737 had been on whiteboards for years, but it was the wrong answer to a now problem. Too costly, too slow, and too risky in the shadow of the 787's painful delays. The board authorized a counterpunch in August 2011. The 737 MAX would graft modern efficiency onto an airframe with 5 decades of service, preserving the 737's type rating, its market lead, and Boeing's margins. Speed and continuity became the guiding logic. Airlines didn't want an airplane that required rewiring their training pipelines. They wanted a cheaper fuel bill next quarter. Boeing marketed the MAX as a familiar cockpit with better economics, up to 14% fuel burn improvement over the 737NG, delivered with minimal disruption. No simulator time became more than a sales line. According to congressional investigators, it became a programmatic constraint, reinforced by contractual incentives. Southwest, a major 737 customer, negotiated a clause that would trigger compensation if simulator training was required, sharpening the internal drive to keep differences invisible to pilots. To square the circle, Boeing pursued an amended type certificate, the regulatory path for derivatives, which allowed much of the 737's existing certification basis to carry forward, with the FAA relying on Boeing's delegated engineers to show compliance on a compressed schedule. From the factory floor in Renton, Washington, the plan looked executable. CFM International would deliver new LEAP 1B engines tuned to the MAX's proportions. The airframe would get aerodynamic tweaks, new displays, and software updates. The assembly lines that had built thousands of 737s would keep humming with only modest retooling. First flight arrived in January 2016, FAA certification in March 2017, and entry into service weeks later with Malindo Air, a Lion Air affiliate. It was an industrial sprint designed to blunt Airbus's momentum while avoiding the time and capital burden of a brand new airplane. And for a while it worked. Orders flowed, production targets climbed, and Boeing executives touted record backlogs and a smooth learning curve. Beneath the momentum, however, the derivative strategy carried engineering debts. The 737's defining virtue, its low stance born of 1960s jetways and baggage carts, left little ground clearance for larger modern engines. The NG generation had already adopted flattened bottom nacelles to make the fan fit. The MAX would need more. Engineers worked within tight geometric limits to meet the fuel burn promise without tripping into a new certification world. The big, efficient LEAP fans had to be mounted carefully. The nose gear was lengthened. Systems were adjusted to keep the aircraft handling within the envelope pilots expected from earlier 737s. Each of those decisions was rational in isolation and essential to the program's business case. Together, they heightened sensitivity to how the airplane would feel at the edges of its performance, and to what software might do to preserve that feel. Those choices were made in a regulatory atmosphere that trusted experienced manufacturers to police their own derivatives. The FAA's Organization Designation Authorization Framework meant Boeing's in-house designees could sign off on compliance findings, with the agency overseeing but not reperforming many analyses. That approach had decades of precedent and helped U.S. aerospace grow. In the MAX's case, it also reinforced the project's central narrative: continuity. If the airplane remained, in essence, a 737, then differences could be smoothed in documentation. If it flew like a 737NG in normal regimes, then pilots could step in with an iPad lesson instead of a simulator slot. Internal messages later released by lawmakers show the friction this created, engineers and pilots testing edge cases while sales teams promised sameness to customers. The tension was not a secret. It was the business model. With the A320neo racking up commitments and early service entries demonstrating real-world savings, Boeing's bet looked necessary and, to many, inevitable. But necessity does not erase physics. The MAX's signature efficiency gain flowed from its engines, and accommodating them on a legacy airframe required geometric compromises with aerodynamic consequences. Those compromises would drive the next chapter of the story: how larger, more efficient engines ended up farther forward and higher on the wing, subtly altering how the airplane behaved when angles of attack grew steep. From the outset, the 737 MAX was a geometry problem disguised as a business plan. The airplane's promise hinged on CFM International's LEAP 1B engines, larger fan, higher bypass turbofans that sip less fuel by moving more air. But the 737's signature advantage since the 1960s, its low stance, left little room under the wing for bigger circles of spinning metal. Previous 737s solved the space crunch with flattened bottom nacelles. For the MAX, even that wasn't enough. Boeing engineers lengthened the nose gear and, crucially, mounted the new engines slightly forward and higher, relative to the wing to preserve ground clearance. On paper, the trade looked tidy, a cleaner, more efficient power plant without tearing up the airframe. In the wind tunnel and later in flight tests, the trade carried an asterisk. At most speeds and attitudes, the MAX behaved like the 737 next generation. It was meant to echo. The differences emerged at the margins: flaps up, manual flight, high angle of attack, places pilots visit briefly in training or during aggressive maneuvering. In those corners of the envelope, the engine nacelles didn't just house thrust, they acted like wings. As the nose rose and the airflow met the bulbous nacelles at steeper angles, the housings generated lift of their own. Because those nacelles sat farther forward of the jet's center of gravity than on earlier models, the extra lift produced a nose-up pitching moment. The result, measured by test pilots and instrumentation, was a subtle softening of the control field. As angle of attack increased, the force needed to pull the yoke did not increase as much as certification rules demand, and in some cases, trended the wrong way. Regulators have a plain requirement for this. The stick force gradient must stay positive, so pilots receive an unmistakable cue that they're moving toward a stall. It's a bedrock of longitudinal stability, built on hard lessons from earlier eras. Boeing's own data, later summarized by investigators, showed that without intervention, the MAX's stick force per G could fall short of Part 25 expectations in specific, repeatable regimes. Flight test crews, flying out of Moses Lake and over the Pacific Northwest, explored those regimes in orange flight suits, easing the jet toward higher angles of attack, recording how the elevator and stabilizer trimmed, and narrating the feel. A lighter than expected pull here, a tendency to keep rising there. To the layperson, it sounds academic. To engineers and regulators, it was a red line. The physics were not mysterious. Moving a large lifting surface forward shifts the balance of moments. Add a modern nacelle's complex flow field, and you change how the wing and tail talk to each other when the airplane is nose high. Designers can counter with hardware, wing reshaping, tailplane changes, or different engine placement. But those fixes cascade through structure, weight, and cost. On a derivative program racing the market, the latitude for such redesign shrank. Boeing made incremental aerodynamic tweaks, but the heart of the problem remained. The MAX needed a nudge to restore the familiar handling cues of earlier 737s without advertising a fundamentally different airplane. That imperative intersected with commercial promises. Airlines had been sold commonality, a MAX that felt like a 737NG, allowing crews to transition with minimal differences training. The feedback loop was tight. If the airplane's natural stability characteristics at high angles of attack diverged from the NG, training footprints could grow, simulator time might be required, and the business case would wobble. Inside Boeing and at the FAA, the conversation turned to augmentation, an automatic limited intervention that could add a gentle nose-down push when, and only when, the airplane wandered into those edge conditions, restoring the stick force gradient and satisfying the rulebook. The solution did not come in a new wing or a taller landing gear, but in software commanding the horizontal stabilizer. Boeing's answer was the Maneuvering Characteristics Augmentation System, MCAS, designed to apply small, targeted nose-down trim so the MAX would feel like the 737 generations before it, in those specific high AOA corners of the envelope. How MCAS was conceived, implemented, and explained would define what happened next. MCAS began as a tidy solution to a narrow problem: how to preserve the 737's familiar handling after geometry changes altered the jet's feel at the edge of its envelope. During early flight tests, Boeing pilots documented that in specific conditions, manual flight with flaps retracted and the nose pitched high, the MAX's control forces were lighter than certification rules require. The fix did not call for bigger wings or a new tail. It called for a small automatic nudge that would restore the positive stick force gradient pilots rely on to sense an approaching stall. Engineers proposed a software augmentation that would move the horizontal stabilizer a few tenths of a degree when the airplane's angle of attack crept into that narrow band, adding a subtle nose-down pressure so the jet would fly, in the pilot's hands, like the 737s that came before it. In Boeing's architecture, that capability lived naturally alongside the existing speed trim system, the behind-the-scenes logic that already uses the stabilizer to help the 737 feel consistent across speeds. MCAS was coded as another mode within the flight control computer, gated by conditions. It would wake only with the autopilot off, flaps up, and high angle of attack. It would sleep the rest of the time. The choice to use the stabilizer, rather than the elevator, reflected physics and precedent. Near a stall, the elevator's effectiveness ebbs, but the stabilizer retains authority. Trimming it in small increments is a proven way to shape control feel without the pilot noticing the scaffolding. In test cards flown from Moses Lake and over Puget Sound, pilots verified that with augmentation engaged, the pull on the yoke grew as expected as the nose rose, meeting both engineering sense and the letter of Part 25. The intent throughout was not to create a stall protection system or a new layer of automation that would manage the airplane for the crew. It was to make the MAX behave like a 737 NG in a corner case most line pilots would rarely, if ever, encounter. That framing mattered. If the change could be treated as a handling qualities tweak, then the MAX could retain the same type rating as its predecessors, and airlines could avoid costly simulator time. Internally, MCAS was described as transparent, a background aid that acted only when necessary and stood down as soon as pilots trimmed or the angle of attack fell. Early design descriptions limited its authority to modest movements at a slow rate, on the order of a quarter degree per second, scaled to the jet's speed, with safeguards that stopped commands if pilots counter-trimmed. But as flight testing expanded, the airplane's nose-up tendency in the most demanding parts of the envelope proved more pronounced than initial analyses suggested. To keep the stick force curve within requirements at higher Mach and higher angle of attack, the program increased MCAS's authority and adjusted its schedule. What began as a small, almost academic correction became a more muscular intervention, still invisible to the crew under normal circumstances, yet capable of moving the stabilizer far enough to be felt if it activated near the ground. The logic also allowed MCAS to rearm and command additional trim if the triggering condition persisted, on the assumption that a genuine high angle of attack event would require persistent stabilization until the pilot lowered the nose. These were consequential choices, shaped by the same pressures that drove the MAX program itself. The system's purpose was circumscribed, the activation window narrow, and the presentation to pilots minimal, all in service of a promise of continuity. In paperwork and briefings, MCAS remained an augmentation to match feel, not a frontline safety net. That categorization would influence how the system was monitored, how much redundancy it demanded, and how prominently it was described to operators. The design trade was defensible in theory, a targeted conditional assist to satisfy handling rules without changing how pilots flew the jet day to day. In practice, its safety rested entirely on the quality and resilience of the data feeding it, the magnitude and timing of its commands, and the crew's awareness of what it might do and how to stop it. In its original form, those pillars were weaker than they appeared. MCAS drew on a single stream of sensor data, could reset and re-engage, and was scarcely mentioned in training materials, choices that would soon prove decisive. MCAS was built to be modest and nearly invisible, but its first incarnation was also fragile. The system's job, as described in certification paperwork, was to add a small nose-down trim input when the airplane's angle of attack grew high in manual, flaps-up flight, restoring the familiar stick force cues of earlier 737s. In practice, its behavior depended on three choices that would later loom large. It listened to a single angle of attack, AOA sensor. It could rearm and command additional trim if the triggering condition persisted, and it was not described to line pilots in flight manuals or routine training. On the MAX, two AOA vanes sit on either side of the nose, each measuring the oncoming airflow's angle and feeding the flight control computers. Redundancy exists to catch failures. If one vane ices, jams, or is misrigged, the other should disagree. MCAS, however, did not compare the two. It took its cue from whichever sensor was tied to the active flight control computer for that leg, without a cross-check. If that single stream of data was wrong, the system would be wrong, by design. Compounding the vulnerability, many MAX aircraft at entry to service lacked a working cockpit alert to flag AOA disagreement. Boeing intended the alert to be standard, but a software logic error effectively tied it to an optional display feature some airlines did not buy, leaving crews with no simple left versus right warning. The absence didn't cause MCAS to misfire, but it stripped away an early clue that the airplane's picture of reality was distorted. The way MCAS acted when it awoke also mattered. Early in development, the system's authority was limited. Small, slow movements of the horizontal stabilizer to satisfy handling quality rules in corner cases. As testing explored higher Mach and higher AOA, engineers increased that authority to keep the stick force curve compliant. The final logic allowed MCAS to move the stabilizer significantly in a single activation, then rearm and command more if the high AOA condition persisted. If pilots counter-trimmed with the thumb switch, MCAS would pause, but if the erroneous AOA value remained high, it could trigger again after a few seconds. A single bad input, thus, had the potential to produce a series of nose-down trim commands. Boeing and the FAA accepted this design on the premise, embedded in hazard analyses, that an unintended activation would be quickly recognized and halted by pilots using the long-standing runaway stabilizer memory procedure and the stabilizer cutout switches on the center pedestal. That premise intersected with the third decision: how much to tell pilots. The MAX was sold on commonality. Differences training for many carriers arrived as a short, computer-based lesson focused on new displays and systems, but did not name MCAS or detail its behavior. In the Flight Crew Operations Manual, the system was generally folded into descriptions of existing trim logic, rather than presented as a distinct function. Boeing's reasoning tracked its certification narrative. MCAS was not a new protection system. It was a behind-the-scenes adjustment that preserved the airplane's familiar feel, acting only where pilots were unlikely to venture. Regulators agreed, and no simulator time was required solely to address MCAS. Internally, as later emails and testimony showed, commercial pressures reinforced the minimization. Any change that risked triggering simulator requirements could carry contractual penalties and erode the MAX's advantage over Airbus. None of these choices taken alone guaranteed disaster. Many transport aircraft use augmentation to shape handling, and pilot checklists exist precisely to tame misbehaving automation. But together they created a narrow, unforgiving path. An erroneous AOA signal could wake a powerful recurring trim command. The system would not ask the other sensor for a second opinion. The cockpit might not display a clear disagreement flag, and crews, unaware a new mode could be moving the stabilizer in the background, were expected to diagnose the problem amid a barrage of warnings and apply the correct memory items within seconds of takeoff. That is the context that framed the first crash. In Indonesia, a single faulty AOA sensor would feed MCAS a lie, setting off a cascade of alerts and trim movements on Lion Air Flight 610 that pushed a busy crew into a fight they hadn't been told to expect, and would be echoed with grim familiarity months later over Ethiopia. Just after dawn on October 29, 2018, Lion Air Flight 610 lifted off from Jakarta, bound for Pangkal Pinang. Seconds into the climb, the captain's control column shook violently, the stick shaker warning of an impending aerodynamic stall, even as the jet was accelerating and the sky ahead was clear. On his side of the cockpit, instruments began to diverge from the first officers. Airspeed and altitude disagree flags, master cautions, an airplane trying to tell two stories at once. ATC cleared the crew to 5,000 feet. They asked to hold there and later to return. The captain flew, the first officer handled radios and checklists. What neither man could see was that the left side angle of attack sensor was feeding the airplane a false picture, telling the computers the nose was pitched far higher than it was. That single bad input woke a piece of software no one had briefed them on. With the flaps retracted and the autopilot off, MCAS concluded the jet was in a high angle of attack regime and began to trim the horizontal stabilizer nose down. The pitch changed. The crew counter-trimmed with their thumb switches. A few seconds later, with the erroneous AOA still high, MCAS rearmed and pushed again. The cycle repeated, more than 20 times according to data downloaded later by Indonesia's National Transportation Safety Committee, KNKT. Each MCAS command shaved the stabilizer farther nose down. Each pilot response trimmed it back toward level. The flight deck was alive with competing cues, a continuous stick shaker on the captain's side, unreliable airspeed messages, altitude disagreements, and trim wheels spinning beside their knees. The autopilot refused to engage. Nowhere in their manuals was there a system name to pin to the behavior. The remedy for a runaway stabilizer on any 737 is a decades-old memory item. Stabilize the pitch, cut out the stabilizer's electric power with 2 guarded switches on the center pedestal, and trim manually with the wheels. On the previous evening's flight, a different Lion Air crew in the same airplane had faced similar symptoms. An off-duty pilot in the jump seat suggested the cutout. They flipped the switches and flew on, reporting the issues on landing. Overnight maintenance replaced the left AOA sensor, a refurbished unit supplied by a Florida repair shop, and cleared the jet for service. KNKT would later report that the sensor was miscalibrated by about 21 degrees, and that the installation and post-maintenance tests did not catch the error. Boeing's own software quirk meant an AOA disagree alert that should have signaled the mismatch never appeared in the cockpit, because the airline hadn't purchased an optional display package. On JT610, the crew did not move the cutout switches. They fought each activation with electric trim while working an unreliable airspeed checklist and coordinating with a busy tower. Twice they handed control between them as workload mounted. The airplane oscillated around its assigned altitude, nose heaving up and down in small arcs, as competing commands alternated. As the flight wore on, the stabilizer crept to a more nose-down position. In the final minute, with thrust high and the trim skewed, the control forces grew heavy. The jet entered a steep descent over the Java Sea and, within about 13 minutes of takeoff, impacted the water with 189 people aboard. Divers would later recover the flight data recorder, and in January, the cockpit voice recorder. Together, they traced a picture of a crew overwhelmed by a cascade of warnings, misled by a single sensor, and kept in the dark about a system that could quietly move their tail. In the days after, Boeing and the FAA issued urgent bulletins, reminding operators of the runaway stabilizer procedure, the first public hint that an obscure augmentation might be implicated. Crews around the world took note, and regulators began asking harder questions about design assumptions and training content. 5 months later, a second MAX would lift off from Addis Ababa with the new guidance in pilots' hands, and face a similar failure under even harsher conditions. Morning broke thin and bright over Addis Ababa on March 10, 2019, when Ethiopian Airlines Flight 302 accelerated down runway 07R, bound for Nairobi. As the 737 MAX rotated, the captain's control column erupted in a continuous stick shaker, an urgent stall warning on the left side, despite the aircraft gathering speed and climbing normally. Within seconds, the flight deck filled with contradictions. Airspeed and altitude flags disagreed between the captain's and first officer's instruments. Master cautions chimed, and flight directors offered conflicting cues. The crew asked to hold altitude and soon requested to return. What neither pilot could see was that the left angle of attack vane had gone haywire at liftoff, pegging to an extreme value that convinced the airplane it was pitched far steeper than reality. While the flaps remained extended, an important safeguard stayed in place. MCAS was inhibited, but as the climb passed the first minutes, and the crew, following normal procedures, retracted the flaps, the software armed. High thrust pushed the jet rapidly through its climb schedule. The erroneous angle of attack value persisted, and reading a phantom approach to stall, MCAS drove the horizontal stabilizer nose down. The pilots countered with electric trim on the yoke. A few seconds later, with the false input unchanged, MCAS re-engaged and trimmed again. The cycle repeated, fewer times than in Indonesia, but with larger bites of stabilizer. Each automatic command increased the forward force required to hold the nose up. Each counter trim arrested the motion only briefly. With the autopilot out of the picture and the left stick shaker rattling continuously, the airplane oscillated around its clearance as the workload climbed. Two features of the moment amplified the danger. First, thrust remained high. Over the high elevation plateau, Addis sits above 7,600 feet. The crew had set takeoff power and never fully reduced it. The jet gathered speed into the overspeed clackers range, and the aerodynamic loads on the tail surged. Second, those loads made the old-fashioned backup, the manual trim wheel between the pilot's knees, nearly impossible to move. The 737's checklists teach crews to cut out electric trim power to stop a runaway and use the wheel to retrim. After Lion Air, Boeing and the FAA had sent bulletins reminding operators of that memory procedure. On ET-302, the crew did move the two stab trim cutout switches, and for a moment the undesired automatic command stopped. But at more than 300 knots with the stabilizer set nose down, the wheel wouldn't budge enough to unwind the trim. A technique taught on earlier 737s, briefly unloading the tail by easing the nose up and down to free the wheel, sometimes called the roller coaster, was not part of modern training syllabi. Under unrelenting warnings, altitude constraints, and a jet racing ahead, the crew re-energized electric trim to help. When they did, MCAS came back to life. The faulty angle of attack still told the brain the nose was perilously high. The software responded as designed, commanding further nose-down trim. The stabilizer moved toward its mechanical limit. The control column force required to oppose it spiked. The captain asked for help. Air traffic control cleared the flight to return, but there was no time or altitude left to sort the crosstalk of alarms, re-establish a normal pitch and power state, and work a rarely used memory item to conclusion. The aircraft entered a steep descent and struck open ground near Bishoftu 6 minutes after takeoff, killing all 157 aboard. Investigators would spend years arguing over the chain of causation. Ethiopia's accident report pointed to a damaged angle of attack sensor, likely struck by an object at or just after liftoff, that fed MCAS a false narrative from the start. France's BEA and the U.S. National Transportation Safety Board agreed on the sensor failure, but also highlighted cockpit decisions that increased the odds against recovery. Thrust left high, airspeed allowed to build, and a partial execution of the runaway trim checklist that ended with reapplying electrical power to a misbehaving stabilizer. Beneath those actions lay the same structural choices that had framed the Lion Air crash. A single-source system that could reset and re-engage, a cockpit inundated with cascading alerts, and crews briefed on an abstract runaway trim, but not on a new augmentation by name. By the evening of March 10th, regulators from China to Europe began parking MAX fleets. 2 days later, the FAA joined them. grounding Boeing's most important product and triggering the most far-reaching safety reckoning in modern aviation. What followed would probe not only software and sensors, but the architecture of trust that let a background system fly blind. Certification shortcuts, internal pressures, and how a fix meant to be invisible became decisive.